Okay, we just have a few more theorems that I want to walk you through here. So theorem 5.5.9 tells us that if we have an inversion and we have a line that contains the center, we know lines not containing the center get mapped to circles that do. Lines that contain the center wind up being invariant, meaning that line gets mapped to the same line, but it's not pointwise. The points on the line shuffle. We'll take a look at that in a second. What else? Any circle other than the circle of inversion is invariant. So we know that circles that pass through the center get mapped to lines, and circles that don't pass through the center go to circles. They're invariant, meaning that circle gets mapped to the same circle if and only if it's orthogonal, intersects at 90 degrees to the original circle of inversion. So let's take a look at those things. So I just have the demonstration in GeoGebra here. So we have the circle of inversion centered at O. We have a line that goes through O this time, and there's a point P on it and P prime. So when I move it around, we see that we always, by definition, P prime is going to be on the line OP, but it moves around. The points aren't fixed on the line, but they get mapped to other points on the line. So the image of this line is the same line, but the points get shuffled. Okay, the theorem 5.5.10 is an if and only if, so we have to look at two different directions. So the claim in one direction is that if the second circle, if I have a circle centered at O there, that's the circle of inversion, I have another circle that's orthogonal. That means if I draw the tangent lines where they intersect, they would be 90 degrees. If that's true, then the claim is that this circle gets mapped onto itself. The points might shuffle, but it gets mapped onto itself. Here's an outline of that. So we can find the intersections of the two circles. Okay, these two circles have to have those two intersections. Okay. P and Q are fixed because they're on the circle of inversion. Remember, P is on the circle, it's going to go to the point P prime, which is going to be right there, so that OP equals the radius squared. Same thing for Q. Let X be any other point on the circle, which we could move around to different places. We could then create the ray OX, which is going to intersect the other circle there at X prime. And then finally the finish of the proof here. So X prime is the intersection of OX and the second circle. Same thing we've seen many times here before. Triangle OXP is similar to triangle OP prime X prime. OXP, this little skinny obtuse triangle, will be similar to OP prime X prime, which is congruent to triangle OPX prime because P and P prime are the same thing. That's just saying those two triangles are equal to each other. P prime and P are the same thing. So triangle OXP is similar to triangle OPX prime. Okay. Since they're similar, we can look at the ratios of the sides. OX over OP is the same as OP over OX prime, setting up the proportional sides. Okay. If we cross multiply, that implies that OX times OX prime is equal to OP times OP. OP is the radius, which is r squared. Okay. That tells us that X prime is actually the image of X because OX times OX prime equals r squared. Okay. So we know exactly where it goes. If we draw, every point on this circle is going to be sent to another point on the circle, and it's the intersection of this ray in the circle. So that proves that direction. If these are orthogonal, then this circle is going to be invariant. The points shuffle, this point goes to here, but the circle's invariant. Let's look at the other direction. Okay, if we reverse that, it says if the second circle is invariant, then they have to be orthogonal. And I've drawn a picture where they're not orthogonal, but we have to prove that they would have to be if the second circle was invariant. And here's just the outline of that. I'm just going to read through there. So if this circle is invariant, other than the original circle itself, there must be internal and external points. So the circle's not the same circle. Things move around a little bit. There has to be some points inside and outside, and we have to have intersections. So consider the line containing O and the point of tangency, R1, so that this line is tangent on this circle. By definition of inversion, R1 prime is going to go, R1 is going to some R1 prime. It's going to be on this line. By hypothesis, R1 prime is on the second circle. We're saying it's inversion. So it has to be on this line and on this circle. Well, if it's a point of tangency, it has to be equal to that point itself. Okay? Which means in this picture, that really has to be the point R. This picture can't look like this. In reality, these circles are going to have to be orthogonal for this to work.